All right. Hello, everyone. I hope everyone can hear me well. So, good afternoon. Welcome to our first live webinar from a series of webinars we will be hosting every month in the next few months. First, let me start by thanking everyone for their interest and taking the time to be here with us today. So it's really appreciated. Today's webinar is about MG Chemicals EMI RFI solutions. Today's presentation has been prepared and will be presented to you by Michael Strong, our lead technical support specialist. Michael has been with MG Chemicals for over 8 years now. He holds a master's degree in physical chemistry and spectroscopy. He has over 13 years of experience in coating characterization and development. He now leads our technical support division and also works in product development and technical sales. Also, Michael is currently pursuing his MBA degree. So now, before we get into our presentation, just a few housekeeping items. The session will be about 60 minutes. We try to keep it that way. So the presentation at the beginning will be about 30 minutes. During the presentation, everyone will be muted, but you can type in your questions during presentation. We will receive those questions on our end, and we will do our best to respond to them at the end of the session. So after the presentation, we will open the floor for a 20 minutes Q&A. The format of Q&A will be the same. So you type in your question and we'll read them out loud to everyone, and then Michael will respond to them the best he can. So please note, we got a lot of questions about this. The whole session will be recorded and published on our website. Also, we will send everyone a download link so you can download the whole session so you can watch it again or have access to it in case you want to go back to it or use it as your future reference. So now, without any further ado, let's get right into it. There we go.
Thank you, Benham, for the introduction, and thank you to those in attendance. We appreciate the opportunity to speak with you about our products. Today's topic is EMI RFI shielding paints. Let's get started. The topic today breaks down into 4 basic segments. First, we're going to look at the basics of EMI shielding. Here we're going to dissect not only the problem, but the solution and how to go about solving EMI. Next, we segue into MG Chemicals solutions, the products that we have to offer, and from there we break down the different chemistries and filler systems available. Knowing this, we now move on to how to choose the right product. And this comes down to knowing how to filter out different requirements and asking the right questions of your customers. And then finally, to finish, we're going to look at the different applications as well as the resources that we have available on our new website. So let's start with the basics of EMI shielding. Now to do this, we're going to consider what we have in front of us as more than just a conversation. Basically, you can look at this as a transmitter and a receiver. The woman in the red jacket is a transmitter. She is producing sounds and words through her vocal cords that she then transmits to the young man on the right, where his ear is able to pick up these signals and translate them into meaningful words in the brain. Now in this particular interaction, the transmitter and receiver are having a conversation which is intended. But let's consider another example. Now let's say she is addressing an entire crowd, but it's not a crowd that she's familiar with. Let's say she sees her friend Bob within the crowd and she shouts out, "Hey Bob." So what's going to happen in this situation? Well, some people may not hear her, and so they don't respond. Some people may not understand English, and so they don't respond. And obviously many people aren't named Bob, so they won't respond either. Now Bob will pick up this transmission, but what if there's another person in the crowd that's named Bob? He may receive this transmission as well, which prompts a response. In this instance, the second Bob who received the signal is an unintended receiver of the transmission. And this is what we can sort of parallel EMI and RFI shielding to. So in the same way that people communicate with one another, electronics communicate by sending electromagnetic signals to the different sensors within the instrument. The drone on the right, for example, is sending out and transmitting electromagnetic signals in which it's able to hover at the proper distance, have the proper speed, and that sort of thing. Now it does so, but it also transmits these signals through open space. Now let's suppose, for example, that the cell phone on the right is able to pick up these signals, and in turn it may in fact invoke a response. In this situation, the response from the cell phone is an unintended one. It's generated not from the cell phone and the cell phone user, but rather from the drone, and this is likely unwanted. This is the basics of EMI RFI shielding and the problem it addresses. It addresses the instance where a machine has picked up an unwanted signal and has invoked a response, and we don't want that. Now, just to be more specific, when we talk about the signals, we're talking about these electromagnetic waves. And if you go back to high school physics, you know that you can break down waves in terms of their wavelength. So a wavelength is that distance defined between the two crests of the wave. And when we're talking about waves, we also have to consider what's known as the frequency. And the frequency and the wavelength are intertwined. They're said to be inversely proportional to one another. And we're going to be mainly dealing with the term frequency rather than wavelength. We'll see this come up later on. So what are the solutions to electromagnetic and radio frequency interference? Well, broadly speaking, the solution is to house the transmitter or receiver in something that's electrically conductive. Now, classically, what they would do is they would house these circuits in either stainless steel or aluminum housing. And the main mechanism for which it is able to protect the circuit is simply that the incoming waves bounce off. In the same way, the circuit that's housed inside the aluminum cavity is also being prevented from generating and leaking out electromagnetic signals that it generates. And so it's not only protected from external sources, but the signals that it's sending are confined to within the housing. However, because of things like weight and cost, materials were switched over to plastic materials, such as ABS, polyvinyl carbonate, these sorts of things. Now, without any kind of treatment, these types of housing materials, the electromagnetic signals would pass right through. So the solution here is to metallize them, and we do that using these EMI conductive paints. Simply paint the interior of the cavity, and now you get shielding from any kind of externally generated RFI signals. Now, another thing to note is how to evaluate properly shielding performance. Now, when we look at shielding performance and effectiveness, it's measured in a unit called the decibel. But it's very easy to confuse this unit, and that's because you can't scale it linearly. It's a logarithmic scale, so here's what I mean by that. Let's take material A and B. A is on the left, B is on the right. So material A at a particular frequency provides 10 decibels of shielding, whereas material B provides 20 decibels at the same frequency. Now intuitively you would think that material B is twice as good, obviously because the unit is twice as much. However, when you look at it in a more practical term, in terms of how effective the material is at blocking the signals, we note that 10 decibels equates to 90% attenuation or effectiveness, and 20 decibels is 99% effective. So while yes, it's double in terms of the value of decibels, it's actually 10 times as effective. So if we continue this trend and we had another material, material C, that had 30 decibels of shielding at that frequency, that material is 10 times as effective as 20 decibels, and it is 100 times as good as a material with 10 decibels. So it's important to realize what the difference in decibels actually means. So now if we look at it in terms of 10 and 70, well, 10 is still 90% effective, but 70 decibels equates to 99.9999%, or 100,000 times as good at shielding. So you can see how this decimal scale can be very deceptive in terms of rating performance. While it may look like a small difference, in fact, it's quite pronounced. And so here's what we end up reporting. And this is a shielding effectiveness graph. So note the x-axis is the frequency scale, frequency going back to those electromagnetic wave we just looked at. And then on the y-axis we have the attenuation. So when you're evaluating a material, what you do is you look at how it performs along a spectrum of wavelengths. Okay, so we've defined what the problem is and essentially what the theoretical solution is. Now let's look at what MG Chemicals has to offer in particular for this problem. Okay, so we're going to start with our AR, or acrylic resin series. And these were really the first kinds of shielding paints to come along. Now they were brought in to shield those plastic housings that I spoke about when they made the switch over from metal parts to plastic parts. So that's sort of their foundation, is as a conductive paint for these shielding enclosures. Now these are great products in that they're easy to use, they cure relatively quickly, and in terms of plastic adhesion, they perform very well. But there's other things to consider that would make them less ideal. So for example, they may not necessarily adhere well to metallic or say concrete substrates. So that's something we need to consider, as well as we need to consider the environment. So in particular, any kind of solvent exposure, whether it's fuel vapors, things like that, it's not really going to hold up in the long term. So something to consider when you look at acrylic resin as a possible solution. Now we have 4 such products that I've listed along with the packaging here, and I'm going to get to that later on. Next, we want to look at our WB, or water-based series conductive paints. And these were designed exclusively to paint the interior of rooms. So it's meant to bond directly to drywall without the use of a primer. We have 3 main products, and again, they're very easy to use. You simply agitate them and then apply them as you would any kind of house paint. Now, some people don't necessarily like the aesthetic of this, and the answer is yes, you can paint over it to give the aesthetic you want with effective shielding. So these are easy to use, they bond very well to drywall, there's no need for a primer, and because they're water-based, they're not only low odor, but they're easy to ship, and that's because they're not flammable. The consideration here is that they do take a long time to cure, and that's because with any water-based product, you need to let it first cure at room temperature before you apply any heat, and this is just to give the film enough time to properly form right. If you rush it, you may in fact cause some cracking, and any kind of gaps in the film will result in poor shielding. Next, we're going to look at a more recent series in the ER, or epoxy resin conductive paints. Now, epoxy typically for a lot of people invoke the idea of a heavy-duty material. That's because they hold up very well to physical as well as chemical abuse. So these in general you can classify as having excellent adhesion to a very wide variety of substrates. These include concrete, masonry, metallic type substrates. But they also survive very harsh environments that other binder systems don't. So for example, if it has exposure to fuel vapors, chemicals, solvents, that sort of thing, epoxy sort of stand out as the product that you want to consider. And we have 3 different products to address those needs. And then finally, we look at more of a niche kind of subcategory, and that's the board level shielding paint. So if you look at the photo on the top there, that is a chip on the circuit board that's been shielded, and it's been shielded to protect the other components within the circuit board, which happens. So this is known as board level shielding. Traditionally, what they would do is a process called canning or metal stamping. However, because of cost and weight, they've switched to using these very low film build paints to provide shielding. So these have excellent adhesion, and typically they can be applied very thin. And I put about 10 microns, but realistically you could probably push around 6 or 7 microns. So that makes them very ideal materials. However, the one caveat I should mention is that these must be heat cured, and some of the heat curing temperatures is exceedingly high, and so that actually rules out certain types of plastics that may necessarily warp at these high temperatures. So just something to think about. Okay, so we've looked at the binder systems. Now, what we also need to consider is the different fillers. So much like pigments give paints their unique colors, these fillers give the paints their unique conductive properties. So we start with the 838. That is a carbon filler, and that's only available in the AR series. So these are good materials for providing shielding up to about, I said maybe about 5 megahertz tops. So low frequency shielding, but mainly people will use them either as just a conductive paint or for electrostatic discharge. Next, we look at the 841, which is a nickel filler, and that gives you like a dark gray matted color. And this is kind of a workhorse material, so it sort of draws a balance between shielding performance and cost. So with a lot of people who may not necessarily know specifics about their shielding requirements, we may start with the nickel just because it may be sufficient for what they need. The other thing is the corrosion protection. And with nickel, it's fairly decent. It does corrode to a certain extent, but it still maintains relatively good conductivity. So at the other end of the spectrum, we have the 842, which is a silver filler. So this provides you with the highest level performance in terms of shielding, in terms of corrosion. The trade-off, of course, is you need to pay for that. This is a very expensive material, and usually we're pretty cautious with recommending it. We like to ask a lot of questions before we go forward just because we don't want the customer to pay more for something they may not necessarily need. And then finally, sort of between the nickel and the silver is the silver coated copper. Now, this is an excellent material, excellent shielding performance, but the one thing that really needs to be taken into consideration is this does not hold up well to moisture, and it will corrode. Depending on the environment, it could be days, it could be weeks, but if you misstep and recommend this in the wrong type of environment, you could have an angry customer within a short period of time. Okay, so now we've looked at all of the different products that MG Chemicals has to offer. Here's the thing though, you have to know sort of how to filter out a lot of noise in order to choose the right product depending on the customer's requirements. And when you come to a lot of websites, you may see something like an eye chart. There's a bunch of different products, but if you have no idea where to start, it can be quite overwhelming. So what we want to do is take this portfolio and condense it down into something that makes a lot more sense. And we do this by splitting up requirements in terms of 4 different quadrants. You can look at substrate and required attenuation more as primary considerations. And then supplemental to this is things like the external environment and the cost, which are more secondary requirements that work more in concert with the primary requirements. So if we look at substrate type, what can we determine? Well, start with plastics. Now, given their ease of use, the practical solution here is the AR series, but I have to caution that plastic substrates don't necessarily do much to filter out the different chemistries, and that's because across the board, pretty much all of our conductive paints will adhere to plastics. So a secondary follow-up question to filter out here is mainly looking at the different types of environment. So if we know, for example, that it was a plastic substrate and it wasn't going to be exposed to anything too harsh, then yes, an acrylic is appropriate, but it may not necessarily be true with other considerations. For drywall, we can look almost instantly to the water-based series, and that's because it was specifically designed for drywall. It adheres well to drywall. You have all the other advantages in that it doesn't smell, it provides excellent shielding, so that's an appropriate choice. And then we come to metals and concrete as the substrate. That sort of points directly at the epoxy resin series. Really, that's the only option here is because the other binder systems won't really adhere that well. So here we can use the information on substrate type to help us filter through some of the different resin systems. Next thing we really have to consider are what are the attenuation requirements. And to do that, we want to know two very specific things. First, what is the frequency range that the device is operating at? What are the frequency ranges that we need to shield against? Now, a lot of the times we will get very direct and specific answers. However, sometimes people may not know. So, in that case, we sort of based on assumptions, and it might be a bit more trial and error to get the right product. And then within that operating range, what is the desired attenuation level? And again, for a lot of people, yes, they can give you specifics and they can give you ranges. Some people may not necessarily know, so then you have to sort of describe the trade-offs, and here's where secondary requirements really come into play. Next, we want to look at the external environment. And with that, we want to look at two main things. One is we want to look at how much moisture is present in the environment. So if it's a freighter out at sea with high salt water content, that basically rules out the use of the 843, the silver-coated copper. And the reason is that over time, this moisture will corrode that product. And once it corrodes, it really starts to lose its conductivity and shielding performance. So there is a workaround if you want to apply a protective top coat over the 843, but for a lot of people that's more work, more cost, so they're not typically interested. So you'd want to look at another filler system. The other thing is whether the paint is going to be exposed to any kind of solvent vapors. And we talked about this earlier. That does not favor the use of things like an acrylic resin or a water-based system. They simply don't hold up long term. So if that's the case, then really you need to consider an epoxy coating. And then finally, we want to look at the cost. And the reason we got to pay attention to cost is because there's so much sticker shock when you consider the bulk volume cost of these materials. So instead, the proper approach here is to also consider the efficiency of the paint to get a better perspective of what it's going to cost to use a certain paint over another. So when we look at the numbers associated with costing for these materials, we have to contextualize it more in terms of the cost per part rather than cost per volume. So to do that, let's consider the examples here. The woman on the left has chosen a more premium paint valued at about $100 a gallon. But then you can judge the efficiency of this paint based on how much of the flooring she was able to coat. The young man on the right purchased cheaper products at $50 per gallon, and having bought the same amount, still was not able to coat the same surface area. So this gives us the same kind of perspective here in that, yes, you could choose a cheaper material, but it may not necessarily save you the money that you think it will, because we have to consider the efficiency of the paint. And here's how we do that. So what we have to consider is getting down to how much each part costs to coat. And to do that, we need to know the surface area of each part and the dry film thickness. Now, the dry film thickness, we sort of give recommended dry film thicknesses, but at the end of the day, a customer is going to have their own sort of process and methods, operator efficiency, that sort of thing. So dry film thickness sort of averages out based on the user more than anything else. And they sort of need to gauge what they're expect in terms of dry mill thickness. So let's for example consider a part measuring 2 inches by 3 inches to give us 6 square inches. We take an off-the-shelf product A, at a cost of $500 per gallon. Now the coverage at a 2 mil dry film thickness is 13,650 square inches. Now we calculate these efficiencies, so that is something that we provide. That is found in our technical data sheets, and we try and standardize it over the same dry mill thickness. So here we're going to use 2 mils. Now let's say 2 mils is also the recommended dry film thickness, meaning that in our opinion you get maximum performance with 2 mils of dry film thickness. So therefore the coverage at the recommended dry film thickness doesn't change. It's still 13,650. The cost per square inch is simply 500 divided by the coverage. Comes out to 4 cents per square inch. and then you multiply it with the surface area, you end up with 24 cents per part. Now let's compare that to a premium product, product B. Product B comes in at $3,500 a gallon. But we need to compare apples to apples. So we start with the coverage at 2 mil dry film thickness. We use the same dry film thickness as we did in product A, just to get that comparison. So right off the bat, we can see that it's closing the gap somewhat in terms of the cost difference because it's slightly more efficient. You can cover a slightly bigger area at 15,570 square inches. But now let's take into account what the recommended dry film thickness is. And maybe this particular product you can apply at a much lower thickness. So in this example, instead of 2 mils, you have 0.8. So again, it's a fraction of product A, and that's going to narrow that gap as well. So when we look at the coverage in terms of what's recommended, now we're almost at 39,000 square inches compared to 13,650 in the first example. The cost per square inch is now 9 cents, and cost per part, it comes in at just 54 cents per part. So you can see how we started at 7 times the cost in terms of the volume, but when we really take into account the surface area, the efficiencies, that sort of thing, we narrow the gap considerably, where it's just a little over 2 times the cost in terms of per part. Okay, the final thing we want to look at are the different industries that this kind of products are used, as well as the different resources that we have available. Okay, so some industries we want to have a look at, starting with aerospace. Aerospace has a lot of instrumentation, navigation tools, instruments, radars, that sort of thing. So it's important that they're properly shielded, so they go through a lot of conductive paint. If you look at the automotive or transportation industry, these have become highly computerized within the last 25 to 30 years. So there's obviously a big demand for shielding materials. The other thing to note here is that they've tended to switch away from heavier metals, stainless steel, aluminum, that sort of thing that would naturally provide shielding. And they're using lighter materials for higher efficiency. So they're using carbon fiber, and these types of materials need to be metallized. And with the efficiency and speed that you can apply conductive paints, that makes them a very popular choice. And finally, when we consider chip and semiconductors, that board level shielding we talked about for shielding individual chips with on-circuit boards, as well as semiconductor fabrication. And so classically what they would do is apply metallic coatings through a process called sputtering. But because of the speed and efficiency that you can apply these conductive coatings, they can be very profitable in the semiconductor industry. The last thing I want to talk about is the resources that we have available. So basically we took on a redesign of our website, and we wanted to make information easier to find and the website to work far more efficiently. So what we've done is we've organized our different categories more like a hierarchical structure. So we start on the bottom, and we have the category data sheet. So the category data sheet would include all of the conductive coatings that I mentioned today, the acrylic, the water-based, the epoxy, that sort of thing. And it provides very broad information about the different chemistries available. Next, we have the subcategory data sheets. So that would be sort of specific to this different chemistries. So there's one for the acrylics, one for epoxy, one for water-based, that sort of thing. So we tend to have a more narrowed focus with the subcategory data sheet when we compare it to the category data sheet. And then finally you have the technical data sheet, and the technical data sheet is product specific. So that will have data concerned with the types of thinners to use, the coverage, viscosity, that sort of thing. So that's more specific information. And then finally, we have an application guide. And the application guide are spread out over the different chemistries. So we have an application guide dedicated to the water-based products. We have another one for the acrylics. And that goes through, different recommended thinners, substrate preparation, thinner ratios, things like how to properly brush, dip, spray, starting recommendations for say automatic dispensing equipment, that sort of thing. So these tools are available through the website and can help give added information that your customers may need. So what do we have to conclude today? Well, EMI RFI is the unwanted interference, and that's caused by those electromagnetic waves that we talked about when it's transmitted from one device to a neighboring device, or in certain situations it could be interference from within the same circuit. Conductive materials like paint that surround the EMI source protect against that interference. And again, we have to be careful when we look at decibel shielding because it's not scaled linearly, so we need to take that into account. MG Chemicals has a full line of EMI shielding paints. We look at it in terms of the different binder systems, so we have the AR, the WB, the ER, and finally the board level shielding, as well as we have the 4 different filler systems, so they're sort of serving different niches. We have the carbon, nickel, silver, and then finally the silver-coated copper. Now in terms of which product to choose, well, to do that we need to ask questions and we need to gather the right information. So we need to know about what substrate we're coating, what are the different shielding requirements, and that goes to frequency as well as required attenuation. And then sort of as a secondary check, we need to look at the external environment and the cost associated with it. And in particular, when we look at cost, we need to consider the cost per part. So we can sort of bypass that sticker shock that a lot of people will see when we price it in terms of volume. So in that respect, we need to know the surface area of the part we're coating, as well as, what kind of dry film thickness would we be dealing with. And then in terms of industry, we have aerospace, transportation, semiconductors. Again, not an exhaustive list. There's also, applications in consumer, telecom, medical, that sort of thing. Okay, so I want to thank you for your time today. My name is Michael Strom. I head the Technical Support Division at MG Chemicals. You can reach me at my primary email listed at the top, or also at the support account, which I check on as well. And if you need to give me a call, my number is listed there at extension 1031. We'll now be taking questions. Thank you very much.
Thanks, Mike. I hope everyone enjoyed the presentation. So as Michael mentioned, so we would like to open the floor for any question. So as I mentioned, please type in your question so we can receive it on our end and we will read it out loud so everyone can hear the question. So while people are thinking about their question or writing them, I just want to have a quick note. So we are planning to host more of these webinars moving forward in the next few months. The next one will be on our conformal coding line, probably next month. So we will release more details soon. So please stay tuned. Also, please share your feedback with us. Tell us how did you like this webinar? Was it useful to you at all, or any suggestion you might have? So we really appreciate and welcome those feedback. It will help us to prepare a better presentation for next time.
Okay, thanks, Benham. So we actually have our first question, and it basically asks, will we be able to share the webinar with anyone that wasn't able to attend? And in fact, we did record this. So the answer is yes. Now, I can't remember how we're going to share those links, but I think we agreed that we'll be able to email the recordings out so that they can be distributed for other people should they
And
want to hear.
also it will be posted and published on our website.
Perfect.
So, but definitely we will send the link as well so people can download the whole session and will have access to it.
Okay. Second question, did you try to coat films? And I'm a little unsure what the substrate type would be. Like, we do sort of venture into more niche applications in textiles and things like that, but I'm not sure exactly what if you wanted to sort of clarify, that would help. So I'm not sure what exactly you mean by coat films.
So apparently it's a polycarbonate
Okay,
substrate.
okay. Yeah, so actually polycarbonate adheres, you can apply pretty much all of the EMI films. Polycarbonate is an easy substrate to bond to, and that's because it's actually susceptible to chemical etching through the solvents that we incorporate into these paints. And what happens is it attacks and it creates a surface roughness, and you need that roughness for the film to sort of latch on and adhere to. So yeah, polycarbonate is in fact a very common plastic type to adhere to. I would say for the most part, you could get away with using an acrylic resin just because it's going to adhere. And again, you have all the advantages of ease of use, quick cure time, good shielding. So that would be my recommendation. Okay. Next question, who is your competition and how do you differentiate yourselves from them? So we have several competitors that are in the business of EMI conductive paint. So they're Parker Hennepin has a division, Comerix, and we look at them pretty intently, but there's also PPG, Spraylat, Atchison. I'm sure I'm missing others, but we sort of keep that internally. Those are some of the bigger players. And, in terms of differentiation, we sort of all converge on similar ideas. How do we, design paint systems that meet different substrate types and different shielding types? So I don't know that too many of our products are exotic. It's one of those things where, you have your version, they have theirs. Ultimately, what happens is the customer ends up deciding what works for them. So there could be ancillary considerations like cost, but what you'll find, I think, with a lot of customers is they would verify the products themselves, both in terms of the usability, and a lot of them will actually perform their own internal shielding test. They won't just take your word for it and saying our shielding at these frequencies is this. So, we're very comparable. I don't like to say we're better, we're worse than, because I don't think it's a zero-sum game in that respect. But in terms of differentiation, I think what we tried to do was make our line more concise and less specific to say use this specifically for this reason, because we know that there's just a wide latitude of uses that you can use any particular paint for. We try and differentiate ourselves, I think, more from a customer experience approach. And I think also with the new website design, we tried to streamline the distribution of information and simplify that. So I hope that answers your question. Have a look at our line, but there's a lot of similarities in terms of how we try and stand out. I think we try and do it more from the customer support side of things. Excellent question, though. Okay, that's a question. Right.
So Mike, maybe I read the next question.
Sure.
So how do you know the film thickness you have applied is correct as per the recommended spec? So it's IM. Yeah. Thank you, Jan.
Okay, so there's a couple of approaches you could take, but ultimately you're basing your assumption that the points that you've measured applies to your entire surface, and really you can't do that with perfect confidence. So there's a few methods you could use. Easiest way to do this is to compare an uncoated substrate to a coated one, and you could use something with micron precision like micrometers. So that's an easy one to incorporate. You simply measure off certain points as a bare substrate, coat the board, remeasure it, take the difference. That's the dry film thickness. You could also weigh a substrate. So by that I mean take the uncoated weight, coat it, cure it, and then take the cured weight. And then the difference is basically you can convert that into a volume. Okay, and you do that by knowing the density of the dry film which we do not provide. You sort of have to ask us for the dry film density. And then with the density, you can convert the weight into a volume, and the volume is the surface area times the thickness. So it's a bit of algebra there, and you could do that. The other more involved method, we'll say, and it is destructive, would be to microsection and do a microsectional analysis. And of course, you can't do this for production parts. So you need to sort of figure out and finalize a methodology, code a bunch of parts, do the cross-sectional analysis, and then sort of figure out, okay, on average, we apply this as a dry film thickness with this level of variation, and just sort of hold it at that. And then what I kind of recommend to a lot of people, if they're sort of speccing in a process, is they don't necessarily have to do it on the parts that they're coating. They could use a ballast part that is probably a lot easier to do this sort of thing. And then they can just sort of correlate that with their coating on their actual parts. So a couple of different options. And I think we did sort of address that in the, well, some of the more recent papers, the white papers that we're writing now. So there are a couple methods, but yeah, it varies basically in terms of destructive versus non-destructive. And there are methods to do that. So if you'd like, you could email me and I could go through it in more detail.
Okay, so the next question is interesting one from David. So I've been working in the coding industry for about 12 years and have only had a call once to have code a room coded. Do you guys get calls for that a lot? Is that
Yeah,
becoming a more
so
common request considering the crazy world we live in these days? Yeah, go on.
I yeah, I'm not seeing it exactly spike, but let's think about where it's applicable. So if you think about a surgical room, well, there they have a lot of tools for monitoring, and this is becoming a lot more computerized. So you'd want something like an operating room possibly shielded. Also, if you've got a server room with information that you don't want to leak out, you could see that. In terms of residential homes, I mean, it's something we see. It's not taking off. I think the most interesting story that we've heard about is an employer who was noticing his employees were taking extended bathroom breaks. And that's because on your cell phone, you can entertain yourself. Well, so his solution wasn't to police it and come off as the bad guy. He simply shielded the bathroom so they weren't able to get cell phone signals in there. So yeah, I think it's going to pick up for sure. I'm not seeing a ton of it in technical support, but that just might be because they're not asking me. It is something to watch though, and I think you'll see it in terms of server room security, medical, in terms of shielding their equipment, and also possibly military.
So the next question is the water-based series suitable to use on wood, in particular electric guitar cavities?
Yeah, a lot of our Amazon reviews actually refer to electric guitar cavities, and that's because they're being used by hobbyists. And the main advantage they like about the water-based paint is they don't have to smell it. So yeah, we do see that in the reviews.
Okay. I think they have a follow-up question from David.
Sure.
Similarly, we have lost businesses due to people moving to cans on board. I never considered that we could coat the cans themselves. I assume they were just made from metal. Is a plastic can then coated with metal something new that is happening, or has this been the case from, uh, sorry, from the inception of the can?
No, so from our research, actually, the metal stamping were metal themselves, and they would either just sort of stamp around it, or they would completely enclose the component with like a molded metal piece. And so the workaround in terms of paint was just to apply the paint straight on the component. So hopefully that kind of addresses. I'm not aware of people putting on plastic enclosures and then painting them. I think, if it was me, I'd say that's just that makes it more cumbersome. Like you're better off just to paint the component itself.
Okay, so we're still getting a question about if the presentation will be available. Yes, it will be published on our website, and we also will send you a link to download the whole session. So that will happen soon. So next question is, what are the largest challenges currently being seen for EMI RFI shielding materials?
I think, yeah, the biggest challenges are miniaturization. So it's less about shielding enclosures and it's more about shielding the circuits themselves. They're becoming smaller, more powerful. And if you look at chip level shielding, you have to be very efficient because there is both cost and weight considerations to this. The other thing I think where we'll see the most growth, and maybe this is deviating a little bit from the question, but I did mention the automotive, and that's because they're going to switch to these lighter, more efficient materials. And so with that, there are issues in terms of how much more the car has been computerized versus now you've switched out these metal components which naturally shield to lighter materials. So I don't know that it's necessarily a challenge. I think it's an opportunity though, where you could see conductive paints really start to take off because they have so many more benefits over things like gaskets and foils and tapes, and that they're easier to apply, but they're also far more conformal in covering areas. So I think, yeah, the challenge will be more at the board level itself, but I think as sort of an add-on to that, the opportunity will be in transportation. Not to say it won't be in everything. I mean, all these kinds of instruments need shielding, but that I kind of see as possibly the biggest opportunity.
Okay, so next question from Samuel. Are the board level shielding paints aimed at the chip manufacturers, or are they aimed for use at the PCB assembly stage?
Yeah, I don't think the manufacturers would be doing the work themselves. I think they would probably subcontract that just because they don't want to bring in paints. Like paints are, they got fumes and things like that. I would think they would subcontract that process to an assembler. Now, the other thing that I did mention was the silicone wafer with those board level shielding paints. And that's because they have that advantage of being applied very thin. And I said 10 microns, but realistically we could push, 6 or 7 microns. So in terms of something to replace sputtering, I think there's an excellent opportunity there if people know others in the semicon industry.
Okay, so the next question from Philip. On circuit boards, is there an automated stencil or masking process used to coat these highly radiated component, or is it done by hand?
I think mostly it's done by hand. I don't know that many people have it down to an automated process, but we're really not in on the ground floor in terms of people doing it. And for the most part, I get questions on, hey, I need to shield, what do I do? And a lot of it's low tech, at least that I deal with. So they'll use painter's tape, or we have a solder mask which you can use that works very well. But I don't know of too many people that have automated it. Like I would think they'd have to use a semi-thixotropic material to apply that, can easily be peeled off. And the solder mask can, but it's pretty low viscosity. So there'd be a little bit of work on how to do that. Whether they've automated it or not, I don't know.
I'm just looking at more question and I don't see anything new. Hold on. Okay, what is the most common methods consumers apply the acrylic coatings?
So it's probably going to be spray, and there's just a ton of advantage with spray that you don't get with other methods, and that's just the overall aesthetic and coverage. The trade-off though with spray is you trade that, I don't want to say efficiency, it's more like time efficiency. But you do sacrifice overall efficiency. So you get a lot more waste. And typically we say that if you're hand spraying, you're going to be about 70% efficient, meaning you take about 100 mils of materials, you'll probably apply about 70 onto your substrate, and the rest will sort of be lost to aerosolization, overspray, that sort of thing. But it does tend to predominate just because it is the preferred method, and you get so much advantage in your overall product. Now with a water base, it's going to be roller brush, and that's exactly how they were intended to be used. Just simply mix it like a typical interior paint, put it out in those roller trays and roller it on. But for the other ones, it's going to be spray.
Okay, so next question from David. To dovetail off the automotive topic, how much conductive paint does MG sell to China?
You're asking the wrong guy. I mean, yeah.
I don't have that information either.
Probably, yeah, not something I'm privy to.
So we do have our sales team on this, but if this is something you really want to know, and so we can also, so we have your contact information. We'll probably get someone from our sales team to give you some information on that.
Yeah, or the other way, they could email the support address,
Yep.
and then I could just pass it along. Whichever works.
Okay, so I think we answered all the questions. I'm just going over them one more time. Yeah, I don't see any new question coming in.
Okay, excellent. Well, those were great questions. Thank you. And again, the presentation was recorded, so you'll have that. And if you have anything further that you think of, feel free to reach out and contact me, and I'd be happy to answer your questions.
Yeah, thank you so much. I want to quickly thank Reggie, our IT director, and Alex, our web developer, who made this event possible. So thank you so much, guys. So, and all, thank you all for attending and taking the time. We hope to see you for the next one.